Our today topic is non-ideal behavior of gases. Any gas which obeys specifically Boyle's law, Charles' law, and general gas equation are under all conditions of temperature and pressure is called ideal gas. There is a factor called compressibility factor which is equal to PV over nRT. If we take 1 mole of a gas, then it will be PV over RT. PV over RT is called compressibility factor. We will plot a graph between compressibility factor and pressure to check the non-ideal behavior of some real gases like hydrogen, helium, nitrogen and carbon dioxide gases at different temperature. We will observe the non-ideal behavior at fixed temperature. So PV over nRT, if we see N is 1 mole and R is a constant and temperature is also constant. So our main variable is PV. If we increase the P, in the same way volume will be decreased, and if we decrease the pressure, in the same way volume will be increased. So overall the value of PV over RT, mean to say compressibility factor, will remain constant, and that is equal to 1 for ideal gases. If the gases show the ideal behavior, then it will follow the horizontal or parallel line of unity at 1 PV over RT, that is compressibility factor value is equal to 1. 1 is for ideal gas. If any gas is behave like ideal, so it will follow the this horizontal line of ideal gas. The deviation from that line will be non-ideal behavior of the gases, and we will see how the real gases will obey or deviate from the ideal gas line. Let's have a look on this. If we plot a graph between pressure at x-axis, compressibility factor on y-axis, then we see the graph that is shown and the temperature is 0 degree centigrade or 273 Kelvin. So we see the behavior of the gases. Helium shows some ideal behavior because it follow the ideal gas line to some extent, almost 250 or 300 atm, and then if we further increase the pressure, it deviate from the ideal line and go up a little bit. In the same way hydrogen show, and then if we see the nitrogen, firstly in the start nitrogen line goes down from the compressibility factor if we increase that pressure, and goes up to the 1.5 of the PV/nRT and some more extent. And in the same way carbon dioxide, it will deviate from the ideal line to too much extent. In the start it goes down to the 0 almost of the compressibility factor, and then it will increase suddenly to the 2 of the compressibility factor value. This is due to non-ideal behavior of the gases because these are non-ideal and real gases. If we conclude the graphical representation of this graph, that hydrogen and helium are more ideal and then the nitrogen and carbon dioxide. And why they are more ideal, we have discussed in a previous lecture, that is Lind's method of liquefaction, that they have hydrogen and helium have small atomic masses and little, almost negligible attractive forces, intermolecular attractive forces, so they are ideal. So now if we increase the temperature to 100 degree centigrade or 373 Kelvin, then if you see the graph, it shows that the gases, the real gases, move to the more closer to the ideal gas line. That is due to increase in temperature. The forces of attraction between the gas molecules decrease down, and so the gases behave more ideally than the previous one, that that is that temperature will be that temperature was 0 degree centigrade and now is 100 degree centigrade. So if we see the graph at 100 degree centigrade, hydrogen and helium behave more ideally, and nitrogen now nitrogen don't show the deviation to the lower side of the compressibility factor, and the carbon dioxide behave like nitrogen in the previous graph at 0 degree centigrade. And these lines, these graphical representation shows that if we increase the temperature, gases behave more ideally. And in the start of the graph, we see that pressure is low, and these lines are more closer to the ideal gas line. Then we can conclude that if we decrease the pressure, if we have lower pressure or decrease the pressure and increase the temperature, then the gases behave more ideally. So in above two graphical representation discussion, we can conclude that that is when gases are ideal at low pressure and non-ideal at high pressure, and in the same way gases are ideal at high temperature and non-ideal at low temperature. These are the two lines which are the conclusion of our discussion. If we decrease the temperature or increase the pressure, then there are appreciable forces of attraction are being created between the gas molecules. So this is a faulty assumption, and the other is actual volume of the gas molecule is negligible as compared to the volume of the vessel. I mean to say that the volumes of the actual molecules the volume of gas molecules actually is negligible, but if we increase the pressure or decrease the temperature or both, then there is no negligible gas molecules volume. We have to consider the volume of the gas molecules. So these are the two main causes for the deviation from the ideal behaviors of the gases. Next we will discuss the van der Waals equation for real gases.